talk is supposed to be the talk where the proof is done, up to the special case of A1, which we'll get to. But I tried, so we had a lot of technical stuff between Lior's talk, where we actually showed like what kind of statement would we want, and why does it prove the Riemann hypothesis. But then there was a lot of technical stuff, and out of fear that a lot of people might have been lost in the technical stuff, I tried to split the talk in two. So the first part is a recollection of the ideas, and somehow a big picture of what's happening, because we are doing something which is actually much more powerful than proving the Riemann hypothesis for a function. We are actually doing something very, very powerful and very beautiful, and I think it deserves a mention. But this first part is not for the experts, because I actually am not completely sure about all the stuff in it, but I did want to mention at least what I think is the big picture here for the people who are less experienced. So if you have like caveats and stuff, where it's great, and I'm not completely sure about the stuff I wrote, so we can talk about it in the afterwards. Okay, so let us recall we have a finite field K, characteristic P, and we choose a prime L, which is co-prime to P. And in the first day, we have constructed the 6-functor formalism for constructible sheaves. Okay, so we will work with Weil sheaves, but I'll suppress this in everywhere, because QL sheaves, like actual constructible sheaves, are a full subcategory of the category of Weil sheaves, and it's stable under all the 6 functors. So any statement we want to prove about Weil sheaves will automatically prove about constructible sheaves, and it will also be conserved by all the operations. So we do not have to worry about this distinction at all. So I will work with Weil sheaves throughout. So in imprecise terms, so this is like a higher categorical gadget, which we didn't explain like all the details, and we intentionally avoided. But in essence, it takes a variety over K, and gives you a Q bar L, a QL bar linear symmetric monadal stable infinity category, which has the property that all the objects there are dualizable. So that's what I call rigid. So rigid means all the objects are dualizable. So it's this kinds of assignment. And for every map of varieties, we have a pair of adjunctions. So we have the star adjunction and the Schrick adjunction. And these satisfy a bunch of compatibility with the symmetric monadal structure. For example, we have proper base change, we have the projection formula, and we have all the dualities, and etc. So this is the thing we had from the first day. Then in the second day, we bootstrapped the observation that when we plug a point, I mean, not a point, a field, a finite field, then if we look at that, so this is symmetric, this is a stable infinity category which also has a heart, meaning we can take cohomology sheaves, which means we can in the categorical terms, it means we have a T structure, and we can take homotopy groups for the T structure. So the heart of this stable infinity category is the category of representations of Z, because this is the Weil group of the field. And representations of Z are very simple. It's giving a number. So using this, we defined a notion of purity, a notion of mixedness, and all this stuff. And then we had the following definition in Lior's talk: a complex of constructible sheaves is mixed of weight smaller or equal to omega if for every I, the cohomology sheaf, the ith cohomology sheaf, is mixed of weight omega plus I. So we denote by DMX the full subcategory of mixed sheaves. So mixed for any weight. And by this lower equal to omega, the category of mixed complexes, right? Mixed complexes of weight smaller or equal to omega, okay? So these are notations. Then first remark is that it's straightforward to check. It's actually a good exercise that the mixed complexes are a thick subcategory. It doesn't require anything but linear algebra. Okay, a thick subcategory means that it's closed under fiber sequences, under 2 out of 3 in fiber sequences, and retracts. Okay. So the Lean purity can now be formulated in the following very generalized form. Okay, so this is the part I'm not completely sure about. Maybe there are like intricacies. But in any case, mixed complexes, which is a thick subcategory for any fixed variety X, are stable under all the 6 operations. So this is extremely powerful. It's like saying that all the operations we can do preserves this very intricate structure of the weights. But even more precisely, we can give, for each of these functions, we can give like a certain extra behavior. We can characterize an extra behavior with respect to the weights. So we will need only the case of F-freak, so I only mentioned the case of F-freak. F-freaks preserve upper bounds on weights. That means it sends a mixed complex of weight smaller or equal to omega to a mixed complex of weight smaller or equal to omega. And I remind you that with, this was mentioned in Leon's talk, that with this normalization, it actually coincides with the statement that we actually want, when we have a proper smooth variety, and we take the cohomology, we want the ith place to be of weight, of the weight plus the I plus I. So this is actually a way to organize this with. So this is an extremely powerful machine, and it also found a lot of applications outside of number theory. So just I will mention 2 things because I think it's good if you're interested in this stuff. It's very interesting, I think, and you can look it up and try to, after the workshop, you can try to see if you can read about this stuff, because I think it's very beautiful. So one thing it was used is by Lustig and the Lean to develop a geometric character theory for finite groups of Lie type. So finite groups of Lie type are points of groups.
So can I ask a small question?
Yes.
So just by dualizing, you get the same statement for all 4 functors. I mean, with the same bound.
Yes, but I mean, dualizing trades upper bounds with lower bounds, and also yes. I'm not completely positive on how to prove that dualizing sheaf is mixed. So that's why I'm a bit hesitant.
Yeah, no, dualizing is not a very good, doesn't have a very good behavior when without assumption of smoothness.
Yeah, but there's a question of whether or not it is mixed. Even.
Whether or not
in particular, it would imply that the lower star preserves mixed sheaves.
Yes.
Is this true?
It is true that all 6 operations written, there's 7 operations there, but all 7 operations there preserve.
Okay.
Preserve. It is true that they preserve mixedness. My entire point was that in general, D might do things to the weights which are a little bit more complicated.
Yeah, it's more intricate to define what does it mean the weight to be greater or equal to something. It's like not the obvious thing. Okay, so by Lustig and the Lean
means that the D has weight lower. It should be equivalent to D having weight lower equal omega or minus omega or something like that. You want to find a kind of. Never mind, it's not important.
I think it's like non-trivial, this dualizing sheaf business, but never mind. We can talk about it afterwards. So Lustig and the Lean used it to develop a character theory of finite groups of Lie type, which are the points of Lie groups over a finite field. And Bernstein and the Lean used this to resolve the Kashdan-Lustig conjectures, which are about representation of semi-simple Lie algebras, which are over C. So this is like very different applications in representation theory, and it's I think it's very indicative of the power of this formalism. So one highly non-trivial, actually, I think it's the main non-trivial, but I don't know about the other parts, so I don't want to say for sure, is actually the Lean Theorem, which says that the special case of Schrick push forward, which was stated by Lior, and this is the fact that for any map of K varieties, a mixed sheaf of weight smaller or equal to omega is sent to a mixed sheaf of weight smaller or equal to omega. Mixed complex, sorry. So we will prove this theorem by first reducing it to a simpler statement about sheaves on A1 using algebraic geometry and the tools we've established so far. And this is the content of this talk. And in the next talk, Stefan will take this simpler statement and prove it using a new idea, which is the Aladic Fourier transform. Okay, so instead of stating the statement about A1, because it's very technical, the statement about A1. So instead of stating it, I will try to prove with you and see where we get stuck. And at this point, we will give Stefan the moshchot. So first, okay, so let's talk about the reductions. So this is the part of the talk where I actually do stuff. So let the psi of f and f denote the proposition that the Lean theorem holds for the map x to y and the mixed complex f. Okay? This is a proposition, can be true or false. So I will now mention all the reductions that can be made, and then we will use them to actually prove to actually reduce the theorem to A1. So the first reduction is somewhat obvious. So if the statement is true for a map F and sheaf F, and for a map G and the push forward of the sheaf, then by just push forward, by using the factoriality of push forward, it is true for the composition of the units. Second, we have extensions. So if we have any map and a fiber sequence, FGH, of mixed complexes, then if the statement is true for F and for H, then it's also true for G. Why is that? Because F freak sends fiber sequences to fiber sequences, and then by long exact sequence cohomology on long exact sequence on the cohomology sheaves, you can just you squeeze G from both sides with the correct weights. So this so feel free to ask questions about this, because this proposition has no proof. I just plan to explain this on the fly. I don't think anything here is extremely untrue. So for suspensions, this is a kind of like a tautology by definition. So if we have a map and a mixed complex, then it's true for the statement is true for F, if and only if it's true for the suspension of F, because suspension all it does is shifts the weights. So
suspension is shifting. What is suspension?
So I don't know what this notation means. So suspension is the colimit of it's a push out of F going to 0, going to 0. This is the definition of suspension.
Okay.
Well, it doesn't matter which direction
It's moving it in one.
It is an if and only if in Shaul's.
Moving in the complex.
It's just moving the complex to the one of the sides, and you don't care which side, both will be correct.
Okay, okay.
The first cohomology of the suspension of F is the zeroth cohomology of F.
Yes.
No problem. Just want to make sure. What's
wait, but
now, what?
I mean, the definition was not invariant under what?
But it doesn't matter. It's the other way.
So the definition was clever enough to be invariant to suspensions, because it's not invariant. The weights is not invariant to suspension. The weights change when you suspend, but the statement is invariant to suspension.
I didn't understand the last point.
So if you take a mixed sheaf, an actual sheaf, not a complex, a sheaf, which is placed in degree 0, then the weight of it as a complex is the same as the weight of the sheaf, okay? But if you shift it, then in our convention, this is not true anymore. Because remember that in our convention, we have this I here. So it depends on where you place your sheaf, because it was cleverly constructed to, yes, okay.
No, so I don't understand. Do you say that like when you shift the eigenvalues change? Are you, like you need them to change?
No, the eigenvalues don't change. The notion of weight change. We define our definition of a weight of a complex.
It's like Q, yes. K to the over 2 or something like this. Like you also normalize with the.
Suspension enlarges the radius by 1.
No, but it doesn't do anything to the actual eigenvalues. It's a formal
Yes.
manipulation. That's
But the radius of what we like the DM, the higher DM that it. Yeah, never mind.
the eigenvalues stay the same. This is a formal manipulation to make it so that it sends, so in the case of a pure smooth variety, it actually preserves the weights. It sends weights to pure complexes to pure complexes. It's just a convention, okay? That's why it's not a terribly important.
I think the thing that is confusing here is not that there is a mysterious like cancellation between what happens with the eigenvalues and what happens with the cohomological shift. Like the eigenvalues nothing happens to them. There is only the shift. The shift doesn't cancel out. But when you push this, if you shift and push, it's like to push and shift. So it's like the same shifts by k. Has nothing to do with the shift being clever. It's just the fact that the shift is constant and preserved, like suspension preserved under pushing.
Exactly.
It doesn't matter what, you could have shifted by k square and it would work.
Yes.
In algebraic geometry, it's like tensoring with the Tate thing. So.
No, it's not. It's not. We are not doing any Tate twists. Suspension is purely at the level of homological algebra. It doesn't do anything to the actual eigenvalues.
Okay, so different point of view. Okay.
So domain excision means that if I have a map and I have an open subset, its complement is S, then if the theorem is true when F is restricted to, sorry, this is an artifact of a previous draft. So if it's true when F is restricted to U and when F is restricted to S, then it's true for F. Why is that? Because we have a fiber sequence that was explained, I think in Shaul's talk, that has F in the middle, and on the left-hand side, you have F restricted to the open set, and on the right-hand side, you have F restricted to the closed set. So if it's true for those individually, then it's true for F. Then you can do the same thing on the codomain. It doesn't matter. It's the same argument. Shows that you can restrict to open subsets in the codomain. And lastly, we have base field extension. Because the notion of weights is independent of base field extension, if I know it for an extension, like if I have a finite field extension and I base changed everything to this extension, then it's true, then it's already true for the original thing. So any questions about one of these maneuvers?
Just making sure that in 4 and 5, it's really important it's shriek and not star, right, for the exact sequence to hold.
Yes.
Okay.
We are pushing shriek.
Yes.
Exactly.
If you wanted, you could have added, you might not need it, but you could have added also the property that the Tate twist also is okay.
I actually had this property, but then I decided I don't need it, so I erased it.
Okay.
Actually,
because there was a question about it, so
yes,
you could just add it.
You could add that you can take twists, and then you can just prove the statement that weight 0 goes to weight 0. Because.
And a bit more generally, you could have also like pulled any sheaf from the base field, right, and tensor with it.
Yeah, this is what I mean by you can prove that weight 0 goes to weight 0. Like the weight doesn't have to be. Yeah. Okay. So let's start the proof. So any question about this before I continue? This or the statement of the Lean Theorem? Okay. So first of all, by Noetherian induction on X, using 3-4, which is the excision, we may freely shrink X and Y. So excision on X and Y, we can freely shrink X and Y's, please. So we can assume that both are affine, smooth, and irreducible. Now, using Noetherian normalization, further shrinking if we need, we can factor X, Y to as follows. So we have a finite map to a fine space. Sorry, this should be an times y. This is a mistake. It should be an times y. And second map is just a projection. Okay? So it suffices to prove individually for R and for pi. Now, shrink push forward along finite morphisms is exact. What does that mean? It means that the cohomology sheaf of R shrink of F is the same as R shrink of the cohomology of F. And it's actually literally computed by summing along the fibers. So if you have a finite map and you do R shrink, then by proper base change, it's actually the stock at any point is the sum of the fibers, the sum along the fibers in a set theoretic sense. So it immediately follows that R shrink preserves purity and weights, and therefore satisfies the Lean theorem, because it actually preserves the eigenvalues. Because you sum along the fibers, preserve the eigenvalues. So it's obvious for finite morphisms. So it suffices to prove the statement for a projection. So we may simplify the projection by factoring it through as follows. And from this, it's enough, so by deduction 1, it's enough to prove the case for a single projection where Y is, as before, smooth, affine, and irreducible. Now, by the visage on F, using the fact that it's a thick subcategory, this the properties suspension and the exact sequences, we may reduce to the case where F is concentrated in homological degree 0, right? So now let's set X to be the support of F, because it doesn't matter, right? We can switch X to be the support of F, and we may shrink X until it's smooth and irreducible as well. So now we have X smooth irreducible over Y, and it's of dimension 1, right? So
where did the A1 go?
What?
Where is the A1?
So X was a subset of A1 times Y, right? Because the support of F is a subset, is a closed subset of A1 times Y.
Okay.
Right? And we can also assume it's a curve. I didn't write it here, but yeah. We can also assume it's a curve because we know it for finite morphisms, right? So, I mean, we can also assume it's a relative curve over Y, because if the map is not a relative curve, so the generic fiber is not one-dimensional, it's zero-dimensional, so the map is finite, like up to like restricting further. So, and we know it for finite morphism, so we may assume that the map is relative curve. So we can factor the map as a Q-fold Frobenius. Now I'm actually not sure about this part. I'm a bit like hesitant now, but I think it's okay.
Sorry
yes,
again. So
okay,
what is X?
So X is the support of F, which we may assume is satisfies two property. It's dominant. It's a dominant over Y, and the map to Y is a relative curve, meaning the generic fiber is one-dimensional. Okay.
Okay.
So now X is a relative curve over Y. So we may factor F as a composition where maximal powers of the absolute Frobenius, and then a map, which is generically reduced. So why can we do this? Right? Because this is to take care of the fact that maps in characteristic P are not generically smooth, because you have the Frobenius. So to take care of this, we have, in the case of curves, so remember that the category of fields is equivalent to...
You don't need this step, because X is already a subset of A1 times Y.
Ah, yes, the map is generically reduced. Remove this. The map is generically reduced because it's a subset of A1 times Y, as Tom said. So
the statement is correct and M equals 0.
Yes, you can do it like that also. And therefore, the map is generically reduced, so we can restrict further to get a map which is smooth. Okay? So we may also assume, like I said before, that the dimension is relative, it's a relative curve. Otherwise, it's finite and we're done, like I said. So
wait,
what?
If the fibers are finite, it doesn't really mean that it's a finite morphism.
Yes, but we can restrict further, right, until we get the finite morphism. A quasi-finite morphism of affine varieties is finite. Am I right? No, I'm wrong. But
No,
it doesn't matter.
But it will be finite over an open subset.
Yeah, it will be finite over an open subset.
Dominant.
It doesn't really matter.
Okay, yes. Thanks.
So also by base field extending until all the fibers are split all into the geometric components, and then doing for every component individually, we can also assume that all the fibers are geometrically irreducible. So now we've reduced to the following case. F is a smooth morphism of irreducible affine varieties.
Wait, can you speak a little bit slower? Why can you assume the fibers are geometrically reducible?
So we can base field extend until the generic fiber splits into all the geometric components.
Okay, yes. Great.
And then we can work individually.
Great, good.
So if F is smooth morphism of irreducible affine varieties, whose fibers are smooth geometrically irreducible curves. So this is the first, this is the thing we reduce to the morphism. And for F, we may assume that it's a pure smooth sheaf. Why pure? Because we can work on the composition series we can work like, it's closed under extensions, this theorem, so we can prove it for pures. And we can also assume it's smooth because any constructible sheaf is smooth over an open subset. So we may also assume. So now we're in this case. Any questions up to this point?
Not a question, but maybe a comment. Maybe you want to go this way at some point, but at any point in this proof, you could have assumed that y is just a point, right, by base change. Just remarking.
Actually, I don't think. I want to prove that. No, I don't.
Oh,
think
no. Okay, fine. Sorry.
I don't think that's true. No, this is not what I want to do.
Yeah.
Any questions?
No, wait. I concur with Stefan's remark. In your list of reductions upstairs, you could have said that if a statement is true at each of the fibers, then it's true at the map.
But it's not true because you need mixed. You need the fact that it's mixed. Mixed is a global property.
No, but it's you said that. Okay, I'm sorry. Also said mixed, not only weights.
Yeah. Okay.
Yeah.
Yes. Okay, that's.
I'm happy that you raised this because this is the exact point now of the proof I wanted to talk about. So, any questions?
So I just want to make sure I understand this last thing. So we could have just talked about like the weights, like the eigenvalues of forbiddians, but the point is that you really need to remember this global condition of being mixed.
Exactly.
To go through the proof.
Exactly.
So okay. So
the tricky part of the proof, the actually trickiest part of the proof is that you are trying to prove something global.
Okay, so just to make sure, it is not true, or at least not a priori clear that it's true, that if that sheaves we just have the correct condition on the eigenvalues without the global condition of being mixed are preserved under under push forward, under Schrick push forward.
Yes. I don't think it's obvious. I don't know if it's true even.
Okay, thank you.
No, wait, I think that's exactly the part that's obvious. I don't agree. Like the fact that weights are at most preserved by lower Schrick just follows from base change. The main difficult part is proving that lower Schrick of mixed is mixed.
I don't think you're correct, Stefan. But
am I not?
Yes, I think you are forgetting that there's a tricky part with real and mixed.
But wait, but if that would be true, that would like then in the Riemann hypothesis part of the Weil conjectures, you don't really need the mixed part. You just need the bounds on the weights. So if that were true, then you would have an easier.
Exactly. That's why I don't think it's true.
Yeah, you're right.
So this whole mixed thing is like an auxiliary notion, which is a global condition that ensures that things preserved under Schrick push forward.
Yes. Very, very good discussion because now I can. So any further question about what was before? Okay.
Can you repeat why the fibers are geometrically irreducible? You can assume this, I mean. Can you repeat why we can assume that the fibers are geometrically reducible?
So I look at the generic point, okay, at the generic fiber, and I base field extend. The base field extend I take a finite field extension until I see all the geometric components. Geometric components is the components of the geometric fiber. Okay?
You mean generic fiber?
I mean, it's a, no, let's say it like this, okay? What's the problem, right? The problem is you can have a variety over a finite field, which is irreducible, but when you base change it to the algebraic closure, it becomes reducible. This is the problem we want to take care of. But you don't have, for any fixed variety, you don't have to take the base change to algebraic closure. It's always sufficient to base field extend to a finite field extension to see all the connected components. And this is what I want to do, but I want to do it for all the fibers. So what I do is I look at the generic fiber and I base field extend until it's geometrically irreducible. I mean, until I see all the connected components, and then I work on each of them individually. So I may assume it is, I may assume that all fibers are
you need to throw away you need to restrict to the open set on which this happens.
Yes, yes. I prove something about the generic fiber, and then I need to move to a small enough open set such that this property holds for it. Thank you. Any further questions? Amazing. Okay.
Yeah, I have a small question. The fibers are like subsets of A1 all the time, right?
Yes, in our case, yes.
Okay.
I mean, yes, yes. Okay, so we will prove it in 2 steps. So, which was exactly mirroring the confusion that was now discussed. We will first prove that the weights of the push forward are correct, meaning they satisfy the bounds we want. And afterwards, we will prove that the sheaf is actually mixed, okay? So why is this allowed? Why is this possible? So the thing that it needs to be noted is that in our reductions, we used certain properties of mixed complexes that allowed us to do the reductions. But the same properties do not necessarily hold for just bounding the mixed stuff, right? So just bounding the weights. We first prove that the weights are correct. So how do we do this? For every y and y, we have by proper base change that the fiber of the cohomology sheaf at I is the ith cohomology with compact support of the curve with coefficients in the restriction of f. So it suffices to prove that for the pure smooth sheaf, G, which is the restriction of f to xy, of weight omega on the curve C, which is the fiber at y, the cohomology has weight omega plus I, okay? So now, what is the case of I equals 0? Since C is affine and G is smooth, we have that the compactly supported this cohomology is 0, something that was never proved but was used a lot. And thus, vacuously has the correct weights, okay? What do we do for I2? For I2, we know that C is smooth. So Poincare duality gives us an isomorphism like this. The global sections, these are the global sections, injects into the product of all geometric stocks. So H0 injects into the product, right? Because if a section is 0 on all the fibers, it's 0. It follows, what?
How, when did we, so why is the -1 there? Like,
so why is the -1 there? Is this comprehensible?
Okay, I see.
So this is the form of Poincare duality for affine curves, affine smooth curves in the L-adic setting.
It follows the wonder comes from the dimension, and it appears in the identification of the dualizing sheaf as QL bar with shift by n, yes, and T twist by n or minus, up to minus in both places.
Okay,
yes.
Yes.
So we identified it explicitly. Like, I think we didn't prove it, but
yes, the thing, let me just be explicit about this, because for the people who are not or a bit confused by this, the thing you have to prove once and for all is that the second cohomology with compact support of A1, you need to relate this to the roots of unity. And I myself am not now sure about whether it's a dual or not the dual, but never mind. So I think the correct thing, I think this is the correct convention, okay?
Shaul, could you just verify again that actually C is just A1?
No, C is not A1 yet. C
Why
is
not?
A1 minus some points.
It's not A1.
No, isn't it a closed subvariety of A1?
It's a closed subvariety of A1. It's not A1.
Okay, so it's either A1 or
An open subvariety.
An open subvariety of A1, sorry. An open subvariety of A1.
why open?
Open. Okay, let me return to this. It was here. X was defined as the support of F, right?
Yes.
But we may assume two things about the support of F. We may assume that it's dominant over Y, okay? Because if it's not dominant, then you can reduce dimension. And if it's, and we may also assume that the generic fiber has dimension 1, because if it doesn't have dimension 1, then by restricting to further open subset, I may assume that the map is finite. And for finite maps, we know the Lean theorem because it's practically obvious. Because it's summing along the fibers. Okay?
Yes, but even before that, X is closed, right?
X is closed subvariety of A1 times Y.
Right.
But
And now you take the fiber.
Y, the generic fiber of the map to Y has dimension 1. So it's open subvariety of A1.
Wait, you're looking at the generic fiber?
X,
I thought that you fixed. I thought that you fixed a closed point.
yes. Once we fixed, so the fiber of this map is A1, right?
Yes.
But we are looking at the fiber from X to Y, and it sits inside A1. It sits as an open subvariety. This is
Well, X is open.
X is open in the fiber of X over a point. This XY, right? XY sits in the fiber of the projection map from A1Y to Y because X sits in this, right?
Yes.
I don't understand. Isn't it the intersection of two closed sets?
Yeah, that's what I thought.
So the fiber.
The support is like, it's the place where it's constant there, right? It's like, it's an open set. I think this is.
Yeah,
like,
so maybe I don't understand. What is the support of F? Maybe
Support,
The
I think
support,
it is-
I don't know. I don't know if I say that, but maybe I was confused. The support is a support. The support is all the points where the stocks are non-zero. This is the support. Right?
Is this an open or
And this
closed
is
or
closed.
some?
So for us, it will be, I mean,
So
it could
it's a
be
closed-
not open and not closed, right? But like, you can assume that it is, I think you can assume that it is open, but it doesn't really
yes.
matter. It's something like,
No, it matters a bit because we are discussing whether the fibers are open or closed subvariety.
no,
of
but we
H1.
can rule
Yes,
out, we can rule out
It's not
the
coherent
fact that it
shifts.
is
It's like
closed. This is
locally,
the point.
it's
Let me say
constructible.
something.
It's not. So
If the fiber is closed, then it's a finite set of points. If it's closed in A1, it's a finite set of points.
John, may I say something? I think that will maybe clarify something. You can do the support thing at the beginning. It's kind of funny to do it here.
No, I don't think I can do it in the beginning. I want it here specifically. I try to do it in the beginning. I'm telling you, it's the combinatorics of this proof is not so nice.
No, you can.
Yeah, but
The steps do matter.
at least my confusion was. Sorry?
You can start you can start the proof by reducing to a subset on which a subset of X on which your sheaf is smooth, and then all the rest of the decomposition you can kind of you don't really need it. You can.
I don't agree actually. You use this factorization. You use this factorization. where x to this is finite. So it's not obvious that you can do this.
I think we
so
don't have
for me,
much
at least
time.
the confusion was that I thought that the support must be closed, but I think now that the support can actually be an arbitrary constructible subset, right?
Can you please trust me that I arranged the proof in a way that is fine, and if you try to change stuff, it will make things worse maybe. So let's try to do it my way and see if it
You're
works.
answering to me, Shaul?
No, I'm telling Tomer. Okay? Afterwards, maybe we can see that it's nonsense.
Do this. Do the way you want. No problem.
Okay. So now let me explain this stuff about the support. Okay? The
So
support of F.
You basically have around 5 minutes. So like maybe
I have what?
5 minutes.
Really? Oh my God. Okay.
Wait. No, wait.
The times correctly.
Stefan stock and Shaul stock were not planned to be the same time. That's the problem. So when you swapped the slots, Stefan stock was supposed to be 45 minutes, and Shaul stock was supposed to be twice than that. So
the topics have not changed. Like
the topics have not changed, but
the speakers have swapped, but the talk topics have not swapped. So
wow,
only the speakers swapped.
The time went so fast. Indeed. I think we should extend it because there's no chance I will finish it in time.
Let's do what you can and not focus on things that we don't have to focus on them right now.
I think you can probably steal a little bit of time from me.
Okay, so we'll see. I guess it will be okay.
So the point is that we are at this point. Okay, let's start from this point, and then we have these statements, right? And we're here. For I0, it was obvious. For I2, we have Poincaré duality. So this has weight minus W because G dual is the linear dual of G. So it has the minus the weights. And so this has weight minus W plus 2, which is W plus 2, which is exactly what we wanted. And now I equals 1. This is lemma 5, which we will come to after finishing this proof. This is the thing that hides the stuff that Stefan will prove. Okay, so we will recall this afterwards, so don't be worried. So now we can embed F as a summand of a real sheaf. How can we do this? We take the sum of F with F dual LB, where B is a Q, an analytic number, such that it's a corresponding complex number is Q to the power of omega over 2. Okay? Because tau is an isomorphism, this number is unique, okay? So I can do this. So this is a real sheaf. Why is it a real sheaf? Because the eigenvalues of this are the complex conjugates of the eigenvalues of this.
What is LB?
LB is a sheaf defined by Lior. It's a sheaf which depends only on a character of the Weil group.
It's like one-dimensional, and the action of the Frobenius is given by B.
Yes.
Yes. Okay.
It's trivial on the geometric.
But so tau is the chosen isomorphism, right?
Yes. It doesn't really matter though. So I will suppress the tau. Okay. For Magnus talk, we learned the highly non-trivial fact that real sheaves are mixed. It just suffices to prove that F lower Schrick of F is real under the assumption that F is real. It's mixing, right? So it's enough to prove that the lower Schrick of a real sheaf is real, right? Because then you have F, it's a summand of a real, then it will be a real, okay? Sorry, it's a summand of a mixed, it will be mixed. That's the point.
So just a small question. The tensor is after the sum, right? Or
this, you tensor with this, and then
then sum. Okay.
Okay, by Grothendieck-Lefschetz, we have this, okay? So the L function of f restricted to xy has this form, where we remember again that this appeared also in Magnus talk. We remember again that the H0 with complex support is 0, because f is smooth. And the restriction is a real sheaf, so the L function is real, okay? So now the roots of the numerator this have this norm, okay? Because the relationship between the norm and the roots of this, it's the inverse of the roots. So yeah, so this was a consequence of this, right? Now, the roots of the denominator have norm which is bounded below by this, because the Frobenius eigenvalues are bounded above by the weight, right? So the denominator and denominator are reduced co-prime polynomials. Why are the co-prime? Because they can't possibly have the same roots, the same roots, because the norm is bounded away from this. So the ratio has real coefficients, so they must also have real coefficients. So that means that it is real. So the weights are real, and therefore the push forward of a real sheaf is real. But we see that F is a summand of a real sheaf, and summands are preserved on the push forward, so it's also true that push forward of mixed is mixed.
I don't understand. I don't understand. So what does it mean for the L function to be real?
Means that it has real coefficients.
No, but
Under tau, like
under tau, I'm suppressing tau.
Okay. Okay.
So now this is the thing we need. Okay. So if you use smooth geometrically reducible affine curve and F is a pure smooth sheaf of weight omega, then the first cohomology of compact support is bounded by weight omega plus 1. This is the thing that was missing in our proof. Okay? So now we record a few reductions. For open subsets, we may shrink U as possible. Indeed, if we have an inclusion of an open subset and a complement, then we have the excision fiber sequence where H is supported on S, and on long exact sequence of cohomology, we get this. The H1 with compact support on a finite set is 0 of dimensional reasons, and therefore the weights of V bound the weights of U. Okay? This is the first easy reduction. Second easy reduction, we may pass to a base of a finite étale cover. What does that mean? If P is a finite étale cover of V, and F is smooth pure sheaf weight omega on U, then the lower shriek of F is smooth pure of the same weight on V. So if the statement holds for V, it holds for U, because we may push further and finish. Now, the last thing, the compactifications. If U is embedded into a smooth compactification with complement S, then we have an excision sequence like this, where J0 is the pi 0 of J star F, it's the zeroth cohomology. This is the underived push forward, okay? And H is this, which is supported on the complement. On long exact sequence of cohomology, we get the following. By the semi-continuity theorem for curves, we know that the weights of H are bounded above by the weights over the open part. So this is omega, so W. So we have sandwiched U between the weights of this and the weights of this. So H, and also this is surjective. So this has weights, I mean, H1 compact support of U has weights smaller or equal to omega, if and only if H1 of C of this thing, the underived push forward, also has weights smaller or equal to omega. So this is like a clever maneuver. Now we do the last reduction. So by the first and second reduction, remember shrinking and passing to a base of an étale cover, we may assume that U is an open subset of A1, because we may always find an étale, small enough open subset has an étale mapped to A1, and F is a smooth sheaf on U that it extends to a smooth sheaf over U union A, where A is some point in the complement. Why are we allowed to do this? Why are we allowed to say that it extends? Well, because if it doesn't extend, then just remove a point. We can always restrict to an open set. Remove a point, and now we have a shift that extends. That's all. So we are in this situation. By the third reduction, it suffices that if J is the inclusion of U into P1, then this thing has weight omega plus 1, right? Because we've seen that it's equivalent, that this thing has omega plus 1 and the compact support has weight omega. So now by a Mobius transformation, we may move A to infinity. Why are we allowed to do this? We may base field extend until we can do this Mobius transformation. We may assume that F is a smooth sheaf on U, which is unramified at infinity. Okay? That's unramified at infinity means exactly this, that it extends to this U union infinity. But this is the last step. We can also assume that F is geometrically non-constant. Geometrically non-constant means that when you base field to the algebraic closure, it becomes constant. Okay? Indeed, if F is geometrically constant, then the underived push forward must be so as well. Why is that true? Because the underived, if you take a constant sheaf on an open dense subset on a curve, and you push forward it underived, then you get a constant sheaf. That's by definition. But the first cohomology of P1 with coefficients in QL bar is 0, right? Because this is a sphere. So the condition of weights holds vacuously. So we can assume that F is geometrically non-constant. And lastly, we can use now the visage as well, and we can assume that F is geometrically reducible by further passing to a base change where all the irreducible components split. So now we're in the situation of this theorem, which Stefan will prove. Let F be a smooth pure sheaf on A1 of weight omega, supported on an open subset, such that it is geometrically reducible. F, this is about F. It's geometrically reducible, geometrically non-constant, and unramified at infinity, and also smooth on its support, which is U. Then the weights are correct, meaning you can bound the first cohomology and the weights on the first cohomology by omega plus 1. Okay, this is the statement. So it's a weird place to end the talk because it's like a very specific statement, but I guess this is the way of things. That's it.
Thank you, Shaul.